If you've got yourself wondering how to design complex enemy AI, you've come to the right place. When I'm designing a game, I generally find myself in the need of scripting an adversarial or an ally agent like NPCs, and I'm often conflicted on what school of thought or what paradigm I could go for when I'm programming these agents. So let's dive right in. Now, talking about enemy AI, what I'm referring to here are agents in your game that behave in an adversarial manner to the player themselves. The pattern of their behavior is generally dictated by the environment or the situation they are in with the player at the moment. Let's talk about it in broader strokes. Enemy behavior AI generally falls into three categories, I believe. You have scripted, passive, and dynamic behavior. Scripted behavior is what happens when you've got a predefined event or right after a cutscene that you want your game to move toward, right? So if you've got your player that's entering a forest, and right as the player crosses the threshold into the forest, you want enemies to spawn on the treetops and drop down and attack the player. It's an ambush. This is a classic case of a scripted behavior because here the way the agents behave is something very subjective and it depends on the kind of game you're making. So I'm not going to go too deep into scripted behavior. Let's talk about passive and dynamic behavior. Now, passive behavior is what happens when your enemy agent is interacting with the environment all by itself. There are no external forces or impulses that influence its decision. There is no player that it reacts to, there are no events that are signaled to it. I call this passive because the way the enemy agent behaves in a typical scenario like this is predefined in a sort of an algorithm that it follows repetitively, probably resting and patrolling and maybe refueling at the base and back to step one. Coming to dynamic behavior, this is arguably the most complex behavioral pattern of an enemy behavior AI. This defines how your enemy AI interacts with the player or any dynamic changes to the game. Say your player character is charging at the enemy. What does the enemy do? Does it dodge? Does it parry? Or does it counterattack? If your player is trying to get away or just escape the arena, does your enemy track it down or chase it and give up after a while? All of that comes under the purview of dynamic behavior. So I'm going to explain how to create and generate passive and dynamic behavioral trees and state machine, because these I feel are the most complex and generic approaches to enemy behavioral AI. So let's get down to brass tacks. How would you go about implementing passive and dynamic behavior in Godot 4.2? It comes down to two paradigms which I find work best: state machines and behavior trees. And hopefully by the end of this video, you'll understand the pros and cons of each, and my personal favorite, working with both of them in tandem. Very powerful indeed, heady stuff. Let's dive right in. So what are state charts anyway? State charts are tools that define an agent's behavior by specifying its attributes at different stages and defining relationships on how they transition from one state to the other. Let me give you a quick example. Say for a simple enemy, you might have a resting state and you might have a defensive state, right? Now the resting state itself has its attributes. When the enemy is at rest, it might be regenerating HP per second. It might also have 0 movement speed, right? And at the defensive state, it probably has +2 attack and again maybe 100 movement speed. Now that you've got your states and you know how your agent operates, in those specific states, you need to define how you transition from one state to the other. So let's say I want to transition from the resting to the defensive state. When would that happen? Well, intuitively it would happen when the player walks in. So when the player is detected, let's just simplify the name. When the player is detected, you should expect to change state, and probably if the player tries to run away, you might have another state, and where the enemy chases it, the chase state. But let's keep it simple for this example. I'm just gonna have two states and maybe two transitions. Let's add another transition back here. Ideally, when would your agent move back to the resting state? I would say that would happen when the player leaves vision, right? So the player leaves vision, and if you want to have an appropriately juicy enemy agent, make it realistic. So I would add probably a 2-second timeout after this, right? So once your player leaves the vision of the enemy agent, it continues pursuing for a couple of seconds and then gives up and moves back to the resting state. This looks good. Okay, now let's talk about another type of defining your enemy behavior, and that is a behavior tree. Now a behavior tree, on the other hand, looks something like this. Or use appropriate units, right? A behavior tree is different in the sense that the way it executes is simplified, and transitions are usually one way, right? So you might have a state like this, and it looks like a checklist. It looks like what your agent does. Let's call this the wandering behavior tree. So how does your agent behave when the agent is wandering? You might have a pre-programmed set of steps here, like walking right, left, north or south, and you might have a couple of random idles and maybe scouting or patrolling. All of these are a sequence of steps which may or may not be complex. When I say complex, I mean they interact with animation nodes and movement nodes. The difference here is your behavior tree does not have transitions, right? It generally executes in a sequential or a parallel fashion. So it might just execute it this way. If I get rid of this, yeah, you might have one behavior tree. So this is how it would look when it's executed in parallel. All three of them execute simultaneously. But you get the gist. The transitions are one way, and there's hardly any transition between states. You generally don't have something like this, and a transition back to parent is also a no-no. What happens is these steps are executed in a defined sequence, and the tree resets and starts over again. So what makes sense where? When would you use a state chart and when would you use a behavior tree? I think a state chart accurately captures the dynamic behavioral AI I mentioned earlier, because here there are transitions that are triggered or are signals that are and events that are being raised from the external environment, from the player or maybe a rock falling or the ceiling collapsing. All of it is external, and this is highly optimized for transitions between states. Whereas a behavior tree while it cannot solve all your problems, it is highly optimized for a series of complicated steps. So say your opponent, the enemy agent, has a double punch kick combo, right? If you want to maintain that in a state chart, you'd need to have separate states for the punching and the kicking and maybe other complicated attacks and maybe a finisher move. And that's why state charts suffer from a problem called state explosion, when the number of your states increases too exponentially and it's hard to manage. And the thing is, between two states you can have only two transitions, but if I add another state right here, how many transitions can you have now? Well, it's 6. The more states you add, the number of transitions possible, they spiral out of control. And oftentimes these states aren't even related to each other. Probably you've got a state where the enemy is drenched, it's wet, or it's not drenched, it's dry. And you've also got unrelated states of being idle and being defensive, right? These states are unrelated to each other. You really don't want to build a state machine where you conflate the two of them and have 4 different states, one for idle and dry and idle and wet, defensive and dry and defensive and wet. So you see the state explosion problem and the number of transitions, how it blows out of control. Marry the two ideas, and let's just say you have a simple state machine as well as behavior tree. When a state is active, you trigger a behavior tree and you leave the transitions to the state machine. You have minimal logic in the state itself, but the states themselves may have behavior tree triggers that triggers a particular tree. So when you're resting, the enemy agent probably wanders around. It's idle and it wanders a bit. And if it's defensive, you have a different behavior tree here. A combat behavior tree. Like I said, this might be a punch kick combo, right? So you probably got left hook and maybe a jab and a roundhouse kick. In order to define your enemy behavioral AI, this works out the best. You leave the dynamic transitions right here and you leave the complicated sequential steps right here. So hopefully this gave you an idea of what we're trying to do. Let's get into the code. So what you see on your screen right now is a prototype 2D platforming, and this shall be our canvas upon which we shall paint our behavioral tree and state machine ideas. So a bit about the project. Before we start, there is a dependency on an asset and a Godot add-on. It's called limboai. It's an excellent piece. I shall link it down in the description, but you can acquire it at the asset library. Just type limboai here, and there are 2 versions. One's for 4.3 and 4.2. I'm on 4.3, so this is the one I have installed. What we have in our game scene is just an arena, and we have our player node here. This is our player with the collision shape and its hitbox, and this is our enemy, our mob. It's an opossum with its hitbox and its hurt box. The red one is the hitbox, the slightly taller one is the hurt box, and these 3 triangles you see here in this M polygon shape is its vision cone. So this is going to be a player character. I have a knockback and basic health setup. Takes damage when it's hit by the enemy. Our mob. We have some basic animations for idle, charging, walking, and like I said, we have the collision shape, the vision cone, the hurt box, and the hit box. Let's fire it up and see what we have so far. So you see the enemy and you see my character. The enemy is unresponsive. It has absolutely no behavioral AI right now, and we do take damage when we collide against it, damage and a slight knockback. So as you can see, I'm 2 HP down, and I think my character dies at 5 HP. Nothing fancy, just Q free it. Let's implement this. This is what I want. This is how I want my character to behave. So first up, you see you've got a resting state and a defensive state. Let's do that. How you want to work with Limbo AI is you have an agent which is going to be acted upon by the AI. What you would do is you create a child node of it. Yep, you see there is a behavioral tree player right here. So let's add a behavioral tree player first, and I'll show you how it works. Now when you hit the BT player and go to the inspector node, you see there's a behavior tree node right here. The agent, it automatically picks the parent, which is the mob itself, and you have a few more settings for when you want it to update. I won't dive too deep into that. Let's create a new behavior tree. When you click the behavior tree, you're taken to this new tab that comes with the extension, which is the Limbo AI editor, right? And how it works is it's basically got a UI that lets you dictate the flowchart of how your behavior tree is going to work. So what I'm going to do now is make up a simple behavior tree like this, right? So let's call this the, let me rename this to, let's call this the root node. And this was a sequence node. Let's add a couple of children. Okay, let's call this the idle subtree, and this is going to be the ponder subtree. This is just arbitrary and very specific to what I'm trying to make. How the sequence node works is it's like a to-do list. It checks off everything, all of its children in a sequential order, right? And you can nest further sequences in that tree. So in the idle tree, first of all, we need to play an animation. We do have an idle animation, right? So let's go back to the tree and play that animation. Yes, so I have created a custom task to play an animated sprite 2D. Nothing fancy. We just select the animated sprite 2D node, and we want to play the idle animation, right? So what it's going to do is it's going to play the idle animation, and then I'm going to play the Wanda animation, and I think the Wanda animation is called walk. So let's go back there, and yeah, let's play walk. Okay, now this isn't complete, but let's see how this works. And spoiler alert, it's not going to work well, and we'll get to it in a minute. Can you see how the opossum is kind of glitched? It's kind of frozen in this state. Why is that? Well, let's debug it. You do have a new tab for Limbo AI, and the entire tree is lit up. Why? Because there is no delay. We're not stopping anywhere, right? We're not specifying a duration for these animations. So it's just flitting between the two of them at an insanely high speed. That's not what we want. So I'm just gonna go ahead and close this, and let me add a time limit, or rather let me add a wait over here. So yeah, let's add a random wait. Oops. Yeah, there you go. So this is gonna wait between 1 to 2 seconds after the idle animation, and I'm just gonna copy this and replicate it here. What does it look like now? Okay, you have an idle animation and you have a walking animation. Not bad. And let's see how it looks in the debugger. Oh, there you go. So it plays idle for some time and then plays the walk animation. Great. But of course, when you're idle, the character needn't move, but when you're wandering, you definitely want it to move. So let's add that real quick. I do have a custom task to wander. So let's do it this way. Wander with a speed of say 50. And this just picks a random direction and causes the agent to move a random direction on the x-axis. Now that we have a wander, we also need to specify how long we want the agent to wander. So let's add a time limit node. So it's gonna wander for 2 seconds, and also I want this to always succeed, so let's do this. Great. What does it look like now? There you go. So the character is moonwalking in a random direction every time. It's idle, moonwalk. We do have a very basic behavioral tree right now, and let's stick with it. And what I'm going to do right now is I go to the behavioral tree player, and I don't want this behavioral tree to be inline. I don't want it to be a part of the scene. So I'm going to save it as an external resource, and let's save it in our AI folder. I'm going to call it the frog mob default behavior tree. Now, like I said, we're done with this. I mean, something quite similar right here. We don't have jump, of course, but we have a wandering behavior. Yeah, since my character doesn't really have arms, I'm going to focus on a charge mechanic. So let's have an alternative tree for charging. I'm going to add another behavioral tree player, new behavior tree. Let's save it right now. Let's call this the frog mob charge, or say engage behavior tree. This is how it engages the player. And the good thing is you can copy this stuff. Let's copy this, paste it right here. So what do we expect from the engage behavioral tree? We don't have an idle node. Let's delete that. And this is going to be called charge. And the animation here we're going to play is, it's going to be the charge animation, right? So let's call it charge. And yeah, let's just leave this for now. Let's just let it probably wander at a higher speed. I'm not going to focus on the direction right now. It may just charge the opposite direction of the player, but that's fine. You get the concept. Yeah, let's save this. So now we have two behavioral trees. Let me delete the first one and see how it works. How the second one works, because you cannot have two active behavioral trees for the same agent. That causes conflicts. So let me delete this one. And now we only have our engage behavioral tree active. So as you can see, the opossum is constantly charging around pretty wildly, and there is no idle. Yeah, there isn't an idle step, so there it goes. I think this should suffice for our behavior trees. Let me go ahead and delete this one as well. The reason I started bottom up is so I could show how the individual behavior trees perform before I head to the state. Now it's time for this, the state machine, which is effectively the orchestrator of the whole thing. Now the thing is, the state machine for Limbo AI utility currently doesn't have too many GUI elements. Right now it's there is a lot of boilerplate code you need to write for transitions and guards. However, it does have a hierarchical state machine node setup. Hopefully this changes in the future. As of October 2024, how this works right now is we need to create a Limbo HSM, which is the hierarchical state machine. Let's go ahead and create that up. And upon this machine, we create states. So you can either create a vanilla state so basically when you create one of these states, you need to write custom logic for it. What you would like, what attributes you would like to have, for example the movement speed and the regeneration I talked about earlier. Or you could hook it up with a behavior tree. So this is what we want because we already have a behavior tree set up. Let's go ahead and create that. This is going to be our resting, and let's create another one. This is going to be engaging. Okay, so what does the resting state point to? It has a behavior tree in the inspector tab. Let's quickly load that. Let's call it the default B tree. And yeah, these are not really important right now. It's also at the engage behavior tree right here. So now what you have is a state machine with two states. But what about the transitions, and what about the initialization? How do you define the initial state? How do you define the parameters? All of that is missing in the GUI. There are additional assets which have better state machines, subjectively speaking, but the Limbo hierarchical state machine right now it's a work in progress, so I'm expecting great things from this, and it also seamlessly integrates with the Limbo behavior tree. So what I'm going to do now is I'm going to access this as a unique name, and we'll have to do the actual setup via the script attached to the agent. So yeah, let's head over to the script. So here I've got a basic script that with move and physics processes. What I'm going to do is, first of all, I'm going to create a new function for initialize HSM. Let's drag this, hold control when you release your mouse, and you get the onReady node. I'm just going to simplify this and call this the HSM. So at this point, what we need to do is HSM dot initialize, and the node is self. you initialize the HSM itself, and also you activate the HSM. Now this method right here needs to be called on ready. Just plug this in here. And by default, it's gonna take the resting state first. Let's see if this works. Yep. So you see the state machine is active and the resting behavior tree is live. You see the pause and wander, rest, wander and rest, and there is no charging whatsoever. And you can quickly verify this by heading over to debugger, and you see that the resting one is actively being run right now, and the engaging one hasn't even been loaded yet. Great. So we're certainly missing something. What is that? Transitions. Like I said, right now, as of October 2024, we do not have UI GUI nodes to define transitions, which I feel is a more maintainable and superior way of doing it. But you can do it via boilerplate code. So let's do that. What you use is the add transition method, and you need to specify the state, the from state, the to state, and the event name, which is going to dictate this transition. So heading back to the diagram, this is the event name, the function. This is the event that when the player is detected, that's when the resting state it undergoes this transition to the defensive state. So you've got your from state, you've got your to state, and you've got the event name, the trigger, right? So that's what it expects here. So let's do that. Let's add these states. I'm gonna add the resting state and the engaging state. Let's just replace this with the percent notation because this is a unique name, and I'm gonna call this resting and engaging state because it's ambiguous otherwise. So I want to transition from the resting state to the engaging state. And when do I want it? When an event called player detected is fired, right? We'll get to that event later. And now I want another transition from the engaging state to the resting state. And this is probably when player has left. There are also a lot of other functionality which I'm not going to gloss over. I'm just going to give it a cursory mention, and that's stuff like your guards, I guess. Yes, you can set guards. What is a guard? Yeah, you. So for instance, your mob has two states, it's resting and defensive. But of course, when you vanquish it, it's dead, right? So there is a dead state as well. And when does it move into the dead state? Only when the HP is below 1, right? So that condition, the HP being below 1, that is a guard. So you might have a probably a dead state here. And you have transitions from both of these states into death, but they do have a guard on top of them that checks for the HP before it transitions to death state. So yeah, let's not build that for this exercise because let's stick to simple transitions and you'll get the gist of it. Okay. Now if I run it, what would you expect to happen? Nothing much. The character doesn't react to the player at all. Why not? Because I just specified events. I didn't really tell the engine what these events are and when are they even going to be fired. So let me turn on visible collision shapes and let's see what our collision shapes look like. Okay. So what I want to happen is when my player enters this red triangle right here, this opossum should basically get triggered and charge, right? And not just this red triangle, I'm talking about this entire M-shaped polygon. Anytime the player is inside this polygon, the opossum should be in the defensive behavior entry state. And anytime your player is outside, it should be in the wandering and idle state. So that's fairly easy to do. The reason being this polygon is the vision cone. So what I can do is I can set up the signal for body entered. And let me also do it for body exited. Okay, so now we have two methods. So when the body enters, I want to check if it belongs to the player. This shouldn't trigger for any random body. I'm so used to JavaScript. And when the player body enters this vision cone, we need to trigger the event, and that uses the state machine dispatch method. So here you basically specify which event just got triggered, and you can add additional parameters and arguments to that method. So here I'm going to use the same. It has to be a string name with the exactly same event name, case sensitive. And let's replicate this for our exited. Let's see what this looks like now. Okay, so right now it's in its wandering and idle behavior tree, and there you go, it's charging instantly. Let me turn off collision shapes. So right now it's idle. When it starts charging, it's going to turn red. There you go. So obviously this is not idle. As you can see, it's super janky. So when the player is above that M of the cone, yeah, you can see how it flips between the states. If my player enters and exits too quickly, it's definitely not idle. But yeah, but it's the backbone of the logic here. And also the reason it's so janky is because I did mention that on this reverse transition you need to have a timeout so it looks realistic, because that's basically what's happening here. We don't have a timeout for it. But yeah, I could probably leave that as a exercise to the reader, as my favorite authors generally tend to. And you can see the opossum murders us in cold blood. How dare you, my own creation. Hopefully this was helpful. Hopefully you got an idea on how to combine state machines and behavior trees to create really robust enemy AI.